Okay, good day. This is the second time I've tried to record this today, and unfortunately, the DocuCam froze up on me, so I'm partially starting over. But this is the beginning of it. So this is lesson 10.2, exponential applications, and we left off at the end of example 1 in most cases. That was well, actually not quite at the end. We're at example 1B for some of the classes, and C for the other classes. I think we just started C. So either you are working on B or C, and you can skip to that when you go back and compare your notes. Skip over this till you find example 1B. See if you completed that. If you did, then go on to C. All right. Okay, so this is on exponential applications. So you're going to be able to use exponential models to evaluate real-world applications. Think word problems. And this video supports Delta Math assignment 10.2 on exponential apps or applications. And you must upload this to me by 11:59 p.m. Saturday. All right. So I just finished writing this stuff out when it all froze up. I almost finished it up. But let's just go through this again. So we have 1, 2, 3, 4, 5 different equations here. They all share one common thing, and that is I should say one particular common thing. There are other common things, and that is they all have an exponent. Okay, and so the exponent is multiplied to whatever the rate is and the principal amount. Okay, and hidden within that would normally be your x in an exponential function. It's just that they're using different letters, and it isn't readily apparent. But that's what these are. Okay. And if you remember, an exponential function is in the form of y equals a times b to the x. So the initial amount is your a. Your b, which includes the growth factor, is over here in the parentheses, and then the x is the the exponent up here. Okay. Now the first equation here is for either exponential growth or decay. So you'll notice there's this plus and minus here. What that means is that you can, if you have 1 plus r, you're going to have exponential growth. Okay. If you have 1 minus r, you're going to have exponential decay. And this is something that is computed annually. So this is an annual thing. And there are some common terms that we have that apply to just about all of these equations. One is r. R is the rate. And that, in this case, for the first problem, equals annual growth. I put grow, but growth or decay computed as a decimal. And that's really true for all of these. They are, wherever you see it, that's what it is. Okay? And when you compute something as a decimal, what you're doing is the decimal itself means hundredths. Okay? So I've written hundredths here to remind you of that. And if you put this into your calculator, so let me turn it on, and I already wrote it in here, or typed it in. 1.34 divided by 100 gives you 0.0134, which is what I have over here. But the other way to do this without the calculator is you just move the decimal 2 spaces to the left. Okay, and so you end up again with 0.0134 in this case, in this example. P stands for principal. That amount means the starting amount, so that's what P is. Here, 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 and you can see it throughout here. And the A is the amount after, and so after so many years, okay? So it's what's left. And it could be it's the amount has grown, or it could be the amount has gotten smaller. It just depends. All right. Now, the first equation is simply exponential growth and decay, and I've pretty much explained that. So you have the rate expressed as a decimal. T is time, and in this case it's going to be in years because this is annual. The next one is a compounding interest formula, and so this is used when you are borrowing money or when you're putting your money in a savings account, and the sum that is given to you or that you put into the bank is accruing interest. The interest is, generally speaking, always compounded, and they're different compoundings. You can compound semi-annually, in which case you notice that the rate is divided by n, and then it's to the nth time. So that's the n is the compounding time, or the compounding, the number of times you compound. So semi-annually, it's 2 times. So you have a 2 down here, and you have a 2 up here in the exponent times whatever the times whatever the time is, and then that's the exponent. And so semi-annually is one you normally see. You can see quarterly sometimes. That's 4 times a year. You could even see daily, which would be 365 days. Remember, though, you've got to keep your times, the units, consistent. So if it's 365 days, then your time is all in days. You want to keep it that way. So be sure you convert. All right, so that's this formula. This one was what we call the PERT formula, and it has this funny dropped E. And that funny dropped E stands for a radical number that is not quite 3. It's like pi over here, okay? So you remember pi is 3.14. This number is, as I say, not quite 3. And you find it, you can find it on your calculator really easily. So let me just enlarge this. And so if you go down here and you look at, let me turn off the light here because I think you can see it better. If you look at the LN button right here, you'll notice that above it there's a little e to the x. If you click the second button at the top, then you'll get e to the x when you type that LN button. So I'm going to do that. So let me bring this back down, and I'm going to click the second button and the LN button, and then I'm going to type in up here. Notice it says e to the. Now they want an exponent, and in this case we don't want a square e or cube e. If it's not quite 2, then it's 2 times, not quite 3 rather. It's not quite 3 times not quite 3 if it's squared, and so on. We just want it to the 1 because we want to know what not quite 3 actually is. So I'm going to put it to the 1, the power of 1, and that's going to give me my answer, which you see is 2.718281828. So you'll notice that looks like it's one of those classic repeaters that goes on forever and ever. 8128, 8128, 8128, 8128. That's what it does. Or 1828 rather. 1828, 1828. Okay, so for purposes of this, since we know we're dealing with something like this, we can estimate it and we can leave it as 3 if that's easier for us. Or we can use it in the calculator. Now in this case, we're going to be doing all of our answers by taking the formula, substituting the values that we get in our problem, and then we're going to actually put it all in this calculator. So we're going to be using this exact version of E. All right, so what's the PERT formula used for? It's used for continuously compounding, or compounding continuously. So this is the initial amount P times not quite 3 and continuously compounding times the rate and time. Okay, that's basically what it is. And the last two formulas aren't used that commonly. This is called the doubling time formula, if you will, because over here, that 2 means you're doubling time. And P of t functions the same way as 8. This is the amount after time has passed. So the amount you're left with. So amount after. Okay? And T of d is the time it takes to double. So this is time it takes to double. All right? And so this P to the O, you'll find it here, and well, let's put it up here, rather. And over here, what that means, what it said, the way you say this, P to the 0 is what it is. P sub 0 is P naught. P naught. And usually this is the way people think of it, but it's really P N-A-U-G-H-T, as in naught T. Okay? And so that's just, what is it? It's the initial amount. Now, don't ask me the history behind why they're using different letters for these terms. Don't ask me, but this is what they're doing. Now, over here, this is what we call a half-life formula. So you see this again for radioactive. You know, when we're talking about decay, you're talking usually about radioactive decay, although not necessarily. And half-life is the same thing. So again, this is P naught, which is again the initial amount. Okay. All right. So ignore this for right now. We don't really need to go over this at this stage. But we will see it used really up here in some of these others where when we get to the problems themselves. Okay? All right, now I'm moving on to the next page. All right, so notice we've got two problems, so I'm just going to divide this down the middle here. And the first one says $9,000 is placed in an account. So anything that's numbers and anything that deals with time, we're going to circle that stuff. So I've got $9,000 here. And it's placed in an account. So this is obviously the starting amount. With an annual, so they tell you an annual interest rate's important, of 8 2/3%. Now let's make sure that I change this because I don't think it's 2/3. Let me look and see. Let me look at my old materials. No, it's 8 2/5%. So let's change that. So this is 8 2/5%. Okay? And they want to know how much will be in the account after 17 years. All right, so that's growth. That sounds like growth because you've got an interest rate and you put it in the bank and it's accruing interest. All right, so which formula do you use? You're going to use the very first formula that we came up with, which is this the growth version of this exponential growth situation. Growth formula, I'm sorry. So I want to do the growth formula. I'm going to go ahead and write it out. So that's going to be A equals P times 1 plus the rate all to the time power, okay? And the interest rate is 8 2/3, so 8 2/5. 8 2/5%. So again, we want to use hundredths. Percent means hundredths. So that's going to convert over, well, let's see what it'll convert to. Let's take 2/5 in our calculator. So that's going to be, turn it on, clear, 2 divided by 5 is 2/5. And you'll see that that's 0.4 or 40%. Now let's use 0.4. Let's forget percents right now. So we also have an 8. So we're going to add 8 to that, plus 8. And so I've got 8.4. So this equals 8.4. But I want to convert it all the way over to a full decimal. So what I have to do is divide this by 100. So divided by, take the answer, divide it by 100, and you're going to get 0.084. So equals approximately 0.084. So I'm going to plug that into what R is. So R equals, or R is approximately 0.084. All right, and P is the initial amount, so that's the $9,000. So let's substitute. We'll put in the initial amount, we'll put in the interest rate, and then the 17 is the time that's in the exponent. So A equals, P is, again, the $9,000, so I'm going to write that in. And then that's times, now remember this is 1. I'm going to make it an old-fashioned 1 with a little cowlick at the top there and feet at the bottom of it. Plus, and then the rate is 0.084. And then that's, the exponent of time is 17 years. It's annual. And now we have our formula completely done. And you'll notice all we really need to do is simplify. We don't need to solve for A by undoing. We just multiply all this stuff together. So, and then of course take it to the 17th power. So I'm going to go ahead and type in here the initial amount, $9,000. And then I'm going to, in parentheses, multiply it to 1 plus 0.084, which is what we have in here. Close the parentheses. And then since I want it to the power of 17, I'm going to click this little caret button. That gives me the exponent, raises it up to a power, and to the 17th power. And I'm going to hit enter. And you'll notice I get 35,460.12865. Well, these are dollars because we started out with dollars up here. So I want cents, and if I were to round 0.12865 to cents, that would be the, to 2 spaces, it would round to 13.13. So our answer is 35,460, and this is dollars, so I'll put the dollar sign up here, and 13 cents. And this is approximate, so I'll put the little wavy line, okay? But it's close. It's close. And if you'll find out in these real world models that, you know, because you're dealing with numbers that are approximations, for the most part, you're going to have answers that are approximations. Now, I'm going to correct myself. This is not an approximation. This is exact, and I'll tell you why. It's because, remember, we said that 2/5 is 0.4. That's a ending decimal, terminating decimal. So this is an exact answer, actually, 0.084. So this is exact. The only thing that's approximate, I guess, is we had those trailing. So I guess it is approximate. Keep it wavy, because we had the trailing answer of it's 35,460.12865. So we rounded it off. So it's approximate. So leave it like that, and you're good. If you are, doing a population of people and you find that your answer is 17.3 people, round it to the nearest whole person, because you're not going to cut anybody up. Okay, so that's one thing that you want to be careful of. Let's look at the next one. So the next one says an element with a mass of 420 grams. So here's 420. That's an important number. And then decays. That's really important. That means you're doing a decay as opposed to growth. By 11.8% per minute time. Okay? How much of the element is remaining after 16 minutes? Now, the good thing about this is you'll notice we have a minute per minute here and minutes here. We can keep this in minutes. We don't have to convert anything. This is decay. We're going to use the same formula, but we're just going to change it. Instead of having this plus sign, we're going to have a negative sign. So we'll rewrite that as A equals initial amount P times 1 plus, no, I'm sorry, not plus, minus the rate to the time power. Okay? And in this case, we have 11.8%. So take the 0.8% and divide it by, well, actually take the whole thing, 11.8, and divide it by 100. So 11.8 divided by 100, and you'll see that we've just moved the decimal over 2 spaces, and now it's 0.118. So convert to decimal, and you get 0.118. Okay? And then now that you've got the decimal, you know what the rate is. You know what the initial amount was. It's 420 grams. And as far as time is concerned, it's got to be the 16 minutes. So substitute. And remember, this is the decimal you want. All right, so the amount after, that's what A is, equals the principal, which in this case is 420, times 1, minus whatever the rate is, which is 0.118 here. And then the time is 16 minutes, so to the 16. Okay? Put it in your calculator. So let me clear this. And so I'm going to type 420, and then parentheses, 1 minus 0.118, close the parentheses, and then put in your little caret for the exponent, type in the 16, and hit enter. And notice you get 56.33, and it goes on. Now on this one, you might want to, you could put it at 56. Again, look to see whatever rounding your question is asking for. This isn't asking for any rounding. And since it is this is probably radioactive decay. You probably want to be pretty accurate. So let's leave it at 56.33. So the amount after is approximately 56.33 grams. Right? Okay, and this was dollars, this is grams. And you know, they may want you to actually go in and give the actual answer as a word problem answer. So they might say, so for instance with A, they could say that the amount left after principal and interest with added interest, something like that, is $35,460.13. And over here, the amount of the element remaining, I'm just taking off the last sentence, element remaining is 56.33 grams. Okay, that's all you need to do. All right. Again, they may just ask for the number. They may also ask for you to write this out, but I suspect it'll only be number and something like delta math. Okay, C, this is where some of my people started to write this out. But in any event, let's go ahead and go through this and figure out what we've got going on in terms of numbers and time. So Gabriel invested, all right, investment, $2,800 in an account paying interest, okay, interest, at a rate of 5.38% compounded continuously, okay. Then it says Eliana invested $2,800 in an account paying interest, so interest again, at a rate of 5 7/8% compounded quarterly. Okay, two different situations. After 15 years, how much money would Eliana have in her account than Gabriel to the nearest dollar? So we started out with Gabriel and Eliana was second. So we're going to just kind of divide this thing down the middle here. And we'll put Gabriel over here. And he has a continuously compounding formula. So that one, if you'll remember going back again to our compounding interest, and if we're compounding continuously, we're going to use the PERT formula, okay? The PERT formula. So the PERT formula is A equals P and then that sub E to the R rate times time power, okay? And let's see here. Let's get back over to my notes where I was. All right, so A equals P sub E to the RT. Really strange looking formula. All right, so we know what A is. E, the principal amount is going to be $2,800, so we're going to write that out. In fact, why don't we do this? This is the equation. Our principal amount is going to be $2,800. And then our rate is going to be 5 3/8. So 5 3/8 percent. Now let's just convert that right now. So we're going to take 3/8 first and then do 3 divided by 8. So turn it on, clear. 3 divided by 8. And that's going to be 0.375. And we're going to add that to the 5. So plus 5. And you get 5.375. And then you want to divide by 100. And you get 0.05375. So I'll write 0.05375. That's the decimal that we want to use. All right. All right. And t is equals what is it? 15 years. 15 years. Okay. So this is going to be A equals 2,800 to the E, and then, or I'm sorry, 2,800 times E, because this is really times E, and then that's to the 0.05375, and then time, the T, because there's a T in it as well. The time we said was 15. So times 15. All right, so let's put this into the calculator. So I've got A equals 2,800. Then I want to multiply that times E. So I go to second, I click the E, and then I put in to the 1, and I close that. Oh, I take that back. I want to do it to the 0.05375 times 15. So let's do that again. So 2,800, and then times E, and then I'm going to put in the parentheses after the caret 0.05375 times 15. So I'm just going to use times 15 and close that parentheses, and hopefully this will work. Aha! So I end up with $6,270.583529. So we're going to have to round that. So A equals, A is approximately, because we're rounding, 6270, and then you're going to round to 2 decimal points, so 0.58. So $6,270.58. Okay. So that is how much is invested by, that's what Gabriel gets after the fact, okay? Now, we have to get Eliana's amount, and then we got to figure out who it says Eliana will have more than Gabriel, okay? And we'll take that for granted until we see it. And then we're going to figure out the difference between the two of them, because that's what they want us to do. You know, how much more money would Eliana have made is what they're asking. So Eliana, now in her case, she's doing a quarterly, right? So quarterly, that would be compounding interest. We'd be using this formula here, where I have P and then parentheses 1 plus the rate over N. N would be 4 in this case, because that's quarterly. That's the number of times it compounds. And then that's to the 4 times, and then, what was it, 15 years? So let's write that out. formula is A equals P times 1 plus R over N to the NT. So this one, Gabriel's, was compounded continuously. I'm going to put this over here, UNDING, continuously. And this is the compounding quarterly formula. Okay. All right, so in this case, P, initial amount, is the same as it was with Gabriel. It's $2,800. They start with the same amount. And then the R is 5 7/8%. Okay, so again, that's hundredths. So we're going to convert that. We're going to take 7/8. So 7 divided by 8. Let's clear this. 7 divided by 8. And that's 0.875. And I'm going to add, or wait, am I adding or subtracting? Yes, I'm adding. I'm going to add 1. Let me see, make sure I did this right. Oh, yeah. I'm going to add 1 to it. Oh, wait. That's not what I'm going to do. I'm going to divide. Let's do that again. So I'm going to take this. So 7/8. 7 divided by 8 is 0.875. I'm going to add 5 to it. That's what I'm going to do, plus 5. So I have 5.875. Now I'm going to divide by 100. And I get 0.05875. So that's going to be my decimal. Okay. All right, and since this is compounded quarterly, and is going to equal 4. Okay, that's the number of times per year that you compound. And we know that the years, again, are the same. It's 15 years. So T equals 15. All right, so the formula, we wrote it up above, but I'm going to rewrite it down here again. So A equals P times 1 plus R over N, rate over the number of compounding times, to the N of T, N divided by T. So A equals, the beginning amount, principal, is 2,800. So I'm substituting now. So P is 2,800, and that's times 1 plus the rate. The rate is the decimal, so that's going to be 0.05875, and that's going to be divided by 4 because 4 is the year N. So that's the number of times per year. And then that's all to the N of T. So that means N, the number 4, times T, and the T in this case we said was 15 years. 4 times 15. Okay? So I should have put that in red, but that doesn't matter. It's not a big deal. All right, so let's go ahead and use our calculator and multiply this all up. So I start out with 2,800. Let's clear this. 2,800 and then parentheses, that's times, 1 plus, and then I'm going to put in parentheses, 0.05875 divided by 4, and then I'm going to close the parentheses. So 1 plus 0.05875 divided by 4. Close the parentheses, and then I'm going to put the caret in for the power. There's the caret, and I'm going to use 4 times 15. So parentheses 4 times 1/5, and that should be the whole thing. Drum roll, please. Dun, dun, dun. I get, that doesn't look right, 2,800. Something went wrong because we started with 2,800. All right, let's go back and see what we did here. Clear. 2,800 times 1 plus, and then let's just do this without a parentheses, the fraction. See if that works. 0.05875 divided by 4. Close the parentheses, and then caret parentheses 4 times 15. Close the parentheses, hit enter. Okay, that's more money. So A is approximately, looks like $6,715, and then it's 0.782921. Okay. Now what I'm going to do is I'm going to go back and I'm going to make this one. So I just made this exact. So let's do exact. I'm going to do this one as exact as well. So this one we had. Let's just do it again. So that one was 2,800 to the E, so that was second E, and then in the exponent spot I have 0.05375, and then parentheses 1, 5, close parentheses, enter. 60, okay, so that's 0.583529. 3529. Now what I'm going to do is I'm going to subtract one from the other. So I've got the 6270 in here. I'm going to subtract yeah, and I'm going to subtract, well, let's do the larger amount. Let's start with let me clear this. So I've got the larger amount, 671.782.921 minus Gabriel's amount, 6270.583.529. Hit enter, and I get 4. Okay, so that the difference is Eliana makes $445. Now we can round. So this is 0.199. That goes up to 20 cents. 0.20 more than Gabriel. So that's your answer, your actual answer for something like this. Okay. Now they might tell you just do it to $445. They may have you just round it to the nearest dollar. Let me see. Oh, it does say to the nearest dollar. It does say that right here. So just leave it like this. Round to the nearest dollar. All right. So that would be the answer you would put in there. Make sure you pay attention to something like this. Because if you don't, your answer's wrong. Okay? All right. I think that's it. That is it. All right, we're done. So let's stop. Have a wonderful rest of your day. Take care. Bye-bye now.